Hello and welcome to a physics tutorial. Today we are going to investigate the electric field at a distance from a line of charges. So as you can see here, here's my line of charges, and then here's the test charge where we are measuring the electric field, and as a distance b from the line of charges. Okay, yes. So there are two assumptions we can make right off the bat when doing this problem that'll make it easier. One of the assumptions is that all of the charges are positive or negative. The other assumption is, the other assumption is that all of the electric field produced vertically by these charges are going to cancel out. So we're going to consider that in a little bit. So let us look at our equation for the electric field. So it's electric field equals kq over r squared, where k is 1 over 4 pi something or another. It's 9e to the 9. Q is the charge, and r squared is the r is the distance from a certain point on the line of charges to the test charge. So we said that when we're finding this total field, we can cancel out all of the vertical components. So we're going to multiply by sine of phi. That's that little Greek symbol there. And phi is this angle here. So the sine will give us just this component moving the charge away, because all the other ones will cancel out. Moving on, let's find sine of phi. Sine is opposite over hypotenuse, and so if opposite over hypotenuse is b over r, but r is just y squared plus b squared, so therefore we get sine of phi equals b over the square root of y squared plus b squared by the Pythagorean theorem. So electric field is dependent on charge, but we are going to need to integrate because the charges are always at a varying distance from the test charge, which is why we need an integral to solve this problem. So the first thing that's going to help us is using something called linear charge density, which is denoted by this symbol, lambda. So lambda, the charge density, is Q over L, where L is the total length of the line of charges. And so if we rearrange that and moved L over to this side, and if we say that L corresponds to Y, and Y is a certain point on this line of charges that produces a certain field, then we can find that dq, or the derivative of q, is lambda times the derivative of y. And now when we plug all of this in, we're finding the derivative of the electric field is k, and then this would have been dq, but now it's lambda dy over, this is r squared, which we found, and then this is sine of phi, which we found earlier. So we know that the derivative of electric field is that. We know that the electric field is the integral of its derivative, and we can write that as this. So we're going to integrate from negative L over 2 to L over 2, which makes sense because the total length is L. Alright, so right off the bat, this is not an obvious integral. My first idea was to do a u substitution, but as you can see, there's no y on top, and we're integrating with respect to y. There's no y on top that would have come from the chain rule, so we can't use a u substitution. My second thought was to try completing the square down here, but that just makes things more messy and complicated. So, we see later on we're going to try to do a trig substitution. Alright, so I remembered that my trig identity, that 1 plus tangent squared theta equals secant squared theta. And I think this might be useful. So we're going to try this. So we're going to substitute b tangent theta in for y. And this is completely legal. That's pretty cool. So not only do we have to substitute in something for y, we have to substitute its derivative in for dy. And so if y equals b tangent theta, then dy must be b secant squared theta d theta. And if you don't know how to get the derivative of tangent theta, it's right here. Let's do this. Yes. So you can pause the video if you forgot how to do that. It's just a quotient rule. So now we substitute in b tangent theta for y, and we get this integral. You notice I've put the limits, the new limits are not negative L over 2 to L over 2, they're negative question mark to question mark. And that's because the limits change when you substitute in a function. So we're going to find that, we're not actually going to find that. There's a trick at the end where you can just solve the equation for theta, and then you don't have to find the new limits, which can be a little bit confusing in my opinion. So as you saw, oh, I forgot to mention up here, these are all constants, so we pulled them out, which will make our lives easier. Alright, moving on. When we substituted in b tangent theta in for y, you notice that we can factor out a b squared. Alright, and if you factor out a b squared, and then you square root it, and then you cube it, and you get b cubed on the bottom. And then this becomes 1 plus tangent squared theta in the parentheses, which that you saw up here is secant squared theta. And now we know that the new integral is going to have secant squared theta d theta on top and secant squared theta to the 3/2 on the bottom. And when you simplify that out, it's just going to be d theta over secant theta, which is just cosine d theta, or cosine theta d theta. And that's a pretty easy integral. It's just sine theta. And we still have the question marks, which is what we're going to solve now. Moving on. Alright, so we started with y equals b tangent theta. If we rearrange and solve for theta, then we get theta equals the arctangent of y over b. And the arctangent is also called the inverse tangent. And the arctangent of y over b is this, is y over square root y squared plus b squared. So you can see that. So what is arctangent of y over b? Well, if the tangent were of the angle were y over b, then it must be this angle here. So, yes. Now, oh, this is actually an angle. This is incorrect. Forget that. Now we move on, and we plug in this value in terms of y that we got for theta. And then this becomes a new definite integral. And you notice I changed the limits back to negative L over 2 to L over 2. And so, sine of arctangent of y over b, well, if we're looking at this angle here, didn't notice that moved. Alright, if we're looking at this angle here, then the sine of that angle is just going to be opposite over hypotenuse, so y over r. And therefore, y over r is this, which is what I wrote up here. That's not the angle, that's the ratio. That's sine of arctangent of y over b. So, we now have this, which is very close to completion. Now we're moving on. We are plugging in these limits. So when we find the total sum of the integration thing, we do the first one, plug that in, L over 2, and then we have the second one, which is negative, but you had to subtract it, so this is overall going to be positive. Even that negative out there is killed by the square down there, and we kept the constants out there. And so our final answer, well, for now, is this. So the electric field at a distance b from a line of charges is this. So 2 times k times lambda, which is the linear charge density, over b, the distance away, times this quantity. So now a common question is, or a common thing we use is, what happens when there's an there's an infinitely long line of charges, and sometimes that's also phrased when the test charge is very close to the line of charges. So in order to represent that, we are going to look at the limit of this function, or this expression, as L, the length of the line of charges, goes to infinity. This becomes enormously large. And so, using the stuff we learned in first week of Calculus 1, maybe, we get this limit, and if you notice here, if L is going to infinity, then this whole denominator is getting very, very close to L over 2. The b squared is just going to be insignificant if this is the square of infinity. So L over 2 over L over 2 is just 1. And therefore we get the final answer with an infinitely long line of charges that the electric field is 2 times k times lambda over b, the distance away. Alright, hopefully that was informative. If you have questions or I made a mistake, you can say something in the comments below, and good night.